Hi, let's say data scientists provide a model to support a new data product. Usually these models are generated using some statistical tools like R or SPSS. So before this model can be deployed in real time, someone needs to implement it using Java, C++, Python, or any kind of general purpose language. Actual is the role of the AI engineer in the data product pipeline. In this video, I'm gonna show some issues about it using the multi-layer perceptron as motivating example. Okay, so in this scenario, let's assume that the data science team want to apply the multi-layer perceptron as model. So our task is to write our version of the neural network. Of course, there exists good neural network libraries, but here we will not use them and code the model from scratch just for simplify. Let's talk about neural network in a nutshell. Neural networks consist of a set of neurons connected by synapses. The neurons are grouped into layers. Every network has input and output layer, but usually they have one or more hidden layers. The synapses are represented by float numbers or weights. Foreign data through such networks is pretty straightforward. Just input values in the input layer and evaluate the state of each neuron by multiply each value by the paired weight. Sum up the values and apply the activation function. There are different kinds of activation functions, but more often the logistical cmake function is chosen. The output of previous layers are the input for the next, and the values held in the last layer is the final output. Foreign data is useful to perform tasks like pattern matching, but how to define the weight values? The best bet is to fit those weights by training the network from data using the backpropagation algorithm. The backpropagation consists of two steps, forward and backpropagation. First, forward the input as we just shown to obtain the output. Then, evaluate the error by subtracting. Now, evaluate sigma for each neuron. Sigma is the product of the error by the value of the derivative of the activation function for the output value. In this case, we have the sigmoid function as activation function, and then its derivative is given by this formula. So, this is the value for sigma for the first neuron. Now we have sigma, we can perform the weight adjust taking as vi the output for the previous layers. Repeat the process for the hidden layers. The point about the hidden layers is that you don't know the value of the expected output. This is the key for the backpropagation algorithm. Instead of evaluate the error as the output layer, for hidden layers you must estimate them using the values of sigma for the next layer averaged by the paired weight. For this neuron, we can estimate the error, sum up the product for sigma 1 and this weight with sigma 2 and this weight, and then obtain sigma for the neuron. Once we have the value of sigma, we can adjust the new values for the neuron weights as before. In order to obtain better results, usually it's included a bias neuron. Bias are similar to neurons, so they have also a weight and you must fit the bias weight as well. Different of a regular neurons, the bias holding value is not evaluated, but a constant value, usually 1. Finally, it's the backpropagation algorithm. It's strongly recommended you read the whole description from the Simon Haikyn book. So before we start coding, let's see what the data scientists have in mind. Here we have a data set with 5 attributes. 4 of them are numeric, and the last one is the class label. The class label assumes just 2 different values, so it seems to be a binary classification problem. Let's check it out on Weka. On Weka we can explore the data. We have 1000 instances, 600 for label 0, and 400 for label 1. Weka can train a classifier for us. Let's choose the multi-layer perceptron and just leave the default parameter values untouched. The training process just finished. We can check the network weights here, but I'm more interested in the performance metrics. The first metric is accuracy. I never make an opinion about the classified performance, just take accuracy because I have no way to know if those incorrect instances are concentrated in only one label value. Better feedback is provided by the confusion metrics. Here you can see that 135 instances for class 1 are wrongly classified as class 0. It is close to one-third of the 400 positive instances. Take a note about these performance issues to ask the data science team about. Uh, Probably they will reply that the data preparation for this product is still in course. So be ready to change your implementation the feature to include that. The metrics above are all derived from the confusion matrix. Save these results because our implementation must perform close to. In the next video, we will code the neural network model presented so far using C++.